All right, welcome to 16.3 Other Properties of Light. We're going to start out with why is the sky blue, how we found out the speed of light the first time, polarization. You've probably heard about polarized lenses. How do they work? The Doppler shift, the stretching of waves due to apparent motion between observer and source. Then I've got two example problems that I'm going to go through. So first, why is the sky blue? When you look up at the sun, you see yellow. When you look at the sky, you see blue. Why is that? It has something to do with what's called Rayleigh scattering. Now, it's scattering because what happens is there's nitrogen in the air, and because of the particular spacing of nitrogen, and that's predominantly what's in the air, it's really good at scattering blue light. So what happens is when white light from the sun's light is actually white, red makes it through, and green makes it through, which we know red and green make yellow, and blue gets scattered. Now these same light, the same white light is coming everywhere. So what happens is over here, red and green make it through, but blue gets scattered. And that blue gets scattered to here. And the same thing is happening in all directions. So that's why every place looks blue and red and green. Now, why does it do that? I'm not exactly sure myself. Now, something else that happens. When the sun sets, it starts passing through more of our atmosphere. And then not only does blue get scattered, now it starts scattering some of the green, some of the shorter wavelengths, or the longer wavelengths. But red still makes it through, and that's why sunsets look nice and red, because of what's called Rayleigh scattering. The speed of light. There's a Danish astronomer called Ole Reamer in the 1670s, early 1670s. He was an astronomer, and he was looking at Jupiter, and he was looking at one of Jupiter's moons called Io. And every day, Io would go around Jupiter, and every day he would watch for when Io would come out from behind Jupiter's shadow. And he noticed that when we were here in January, or whatever, he noticed that there was a 22-minute difference. It was coming out like clockwork. Then over here, there was like a 22-minute lag, and he said either Io is tied to Earth's orbit around the sun, or it takes light 22 minutes to get across that distance, and he was right. He used good old velocity equals distance over time, and he knew the distance, and he knew the time, and he came out with the speed of light to be 2.2 times 10 to the 8th meters per second. Now, that's really close. The accepted value of the speed of light is 3.00 times 10 to the 8th, or if you're really good, the actual value of the speed of light is 299,792,458 meters per second. Now, this will never change, even as we get better and better and better at measuring the speed of light. It doesn't get any, no decimal points will get tacked on. What happens is we will actually adjust the meter to make it fit. So this is the exact speed of light all the way out to infinity. It's kind of neat how that works. There are many other people. We use interferometry and cavity resonance. I'll actually show you some cavity resonance tomorrow. We'll calculate the speed of light with a microwave. Kind of fun. Polarization. Now, you've undoubtedly heard about polarized sunglasses. And here's a view. This is a lake with polarized, and this is a lake without. And you'll notice that this is totally blocked by the glare. With polarized sunglasses, you can see through the glare. Now, how does that work? First of all, normal, what's called ambient light, vibrates in all planes. You can think of a polarizing filter as a fence, and they have a fence right here. These fences are either vertical or you can make them horizontal. So what it does is it cuts out and it only allows waves that are vibrating vertically to get through. Now, if you were to take your fence and align them at 90 degrees to each other, you can cut out all light, so nothing gets through. And that's what you see in these two cases. If the fences are aligned, you get light through. If the fences are not aligned, you get nothing through. And this is actually how 3D glasses work. There are two images projected on the screen. I'm using blue and green. And what it does is you have a horizontal filter and a vertical filter. So each eye gets to see its own image, and that's how you get stereoscopic 3D images. The Doppler shift. The Doppler shift is in light as well as sound. These are the equations up here, frequency and wavelength. Now, when things move away from you, as you see right here, it gets stretched out, and we call this a redshift. If things move towards you, we call this a blue shift. The frequency goes up, the frequency goes down, just like in sound. Now over here, a very clever man named Dr. Erwin Hubble noticed that every star he looked at was redshifted. Stars that were very close up, there was a signature. And if stars, the farther away a star was, that same signature was present, but it was just shifted towards the red. And he said, things that are far away are moving faster and faster. And this is what's called the expansion of the universe. He discovered that the universe was expanding because of the redshift. Here, what I've got an astronomy and a light bulb. And I'm going to make the universe expand between them. And that expansion is going to stretch out the wave. So not only is the star moving, the star is not moving away from us, the universe itself is expanding. It looks like it came from some point, some big bang. The universe is expanding. That is why we have redshift. And that's pretty amazing. Here I've got another example. If you move away, you can see the two spectrums. The faster I go, the farther to the right the top one gets and the redder my star gets. Or I can move towards you and it's going to get bluer. And this is exactly why, this is how we hunt for aliens. Here we are on planet Earth. And when we see a planet going around a star, what it does, the star makes the planet makes the star wobble. So when the star goes towards us, it gets blue shifted. And when the star goes away from us, the light from the star gets red shifted. So what we do is we look at the color versus time for a star. And if it does this, we know there's something orbiting it. Something is pulling this star to make it wobble, and we can figure out where that planet is, how big the planet is, how far away it is, how long it takes to orbit, all from dissecting the light that comes from it. The light tells us a great deal about the planet. Last, how do you relate frequency to wavelength? Well, this goes back to last chapter and the chapter before. You just plug everything in right here. The velocity is the speed of light. The wavelength is 513. Now be careful. This is in meters per second, so we got to make sure that this is in meters. So we go 513 times 10 to the negative 8. That's what a nanometer. Times 10 to the negative 9th. Because nano sounds like 9. So now all you do is you pull out your calculator, divide these two numbers, and we got it. So 3 times 10 to the 8th divided by 513 times 10 to the negative 9th. We get a pretty big number. 5.85 times 10 to the 15th. Now that's Hertz, Hz. Number 15, the next example. This deals with the Doppler shift. It says a hydrogen atom in a galaxy moving with the speed of this away. That's important. It's moving away from us, so it gets redshifted. It emits a light with this frequency. What frequency of light from that hydrogen would be observed by astronomer on Earth. I just pulled this equation from my other slide, and I'm going to plug everything in here. So we're looking for what frequency observed. What would be observed? So we're looking for this. This is this frequency here, 6.16 times 10 to the 14th. 1 plus or minus, oh, what the heck? V is the speed, so 6.55 E6. C is the speed of light, 3.00 e to the 8th. Now, we've got to figure out, do we add or do we subtract? So we've got this thing and it's giving off light, but it's moving away from us, so we know that it gets stretched out or redshifted, which means that my frequency goes down. So I want this number to go down. The only way that this is going to go down is that if this big quantity right here is less than 1. So to make it less than 1, I know that I just have to subtract. If I was going towards it, I would add, and it would be blue shifted, and the frequency would go up. So now all I do is I plug it in with that subtraction in there. So 6.16 e to the 14th times 1 minus 6.55 e to the 6th divided by 3 e to the 8th. 6.03 times 10 to the 14th. Oh, that seems right. Because it did go down, and that's what I expected to do. So I subtract to make it go down, I add to make it go up. All right, I think that's everything I've got for you. Maybe I'll show you one other interesting website that I found. This shows Michelson. Your book mentions how other ways to find the speed of light. There was this guy named Michelson, and what he did is he used an octagonal mirror that was rotating, and he shined light off of this mirror, and the light would hit this mirror, bounce over here, bounce back, and bounce at a detector. Now, if he rotated the mirror too slow, which you're seeing here, the light would not make the detector. If he rotated the mirror too fast, it would hit on the other side of the detector, and that's not good. So what you do is you just start adjusting until you get the detector starts detecting things, and then you can relate that rotational motion and that distance to the speed of light, and you can find the speed of light. And so he did this in the 1890s, early 1890s, to find the speed of light. And these were on opposite mountains, mind you. This is a really quick little setup. But what he did is he set it up on mountains that were 35 kilometers apart. Your book goes into a little bit more. So